Okay. I think we got it now. All right. So we are on, this is twos, right? That's number 3. Okay, so we've done rectangles, rhombuses, parallelograms, triangles. Then we looked at trapezoids in notes number 2. Next up is regular polygons. Okay, do we remember what a regular polygon is? Do you guys remember? What's it mean for a polygon to be regular? Nod your head. Yeah. It's regular. No? Nothing? Means all the sides and all the angles are all the same. They're all congruent, right? So, oh, why did it turn off? Sorry. So that means that the sides and all the angles are the same. So the first type of regular polygon is an equilateral triangle, okay? Now, you guys already know a formula, area equals 1/2 base times height for triangles. There's another one for an equilateral triangle. You don't have to memorize this, but in certain types of problems, it's really helpful. And it comes from the fact that if I've got an equilateral triangle, right, then that means all 3 sides are the same. So this would be side, side, and side. And if I wanted to find the area of that, I'd have to drop in a height or an altitude, right? And because this is a equilateral triangle, that means all 3 of those angles are 60 degrees. So that means that this is a 60-degree angle, and then this is a 30-degree angle because that altitude splits it in half. So then this, like, part of the side, this would be 1/2 of S over there. Do that in a different color so we can see it better. All right, so this would be 1/2 S. And then if I use my 30, 60, 90 rules, that would make this height S radical 3 over 2. It'd be 1/2 S times radical 3. That's the height, right? So then if I do 1/2 the base, which is S, times the height, which is S radical 3 over 2, then we end up with a formula that is S squared radical 3 over 4. Okay, so if you know you have an equilateral triangle, you can also use that formula. You can still use 1/2 base times height, still works, but it's a little bit of a shortcut for equilateral. It's helpful. It's helpful for a problem like this where it says the area of an equilateral triangle is 48 radical 3 square feet. What's the perimeter of the triangle, right? If I use the 1/2 base times height, I have 2 variables I don't know. I don't know the base and I don't know the height. I could kind of draw my triangle and split up the sides and try to figure it out. But if I know this other formula, it goes a lot quicker. So if my area is equal to S squared radical 3 over 4, then I can plug in the part I know. So 48 radical 3 is the area. That's going to be equal to S squared radical 3 over 4. I can multiply both sides by 4. So I just get S squared radical 3 on that side. 48 times 4 is 192 radical 3. I can divide both sides by radical 3, which would just get us 192 equals S squared. And then if I take the square root of both sides and simplify, we get that a side length is 8 radical 3. So then if I want the perimeter of that triangle, I just take that 8 radical 3 times 3 sides of the triangle, which is 24 radical 3. Okay. But again, you have to memorize that formula. It's useful sometimes. I think sometimes they give it to you, like on the SAT. Sometimes they'll tell you area of an equilateral triangle, but not always. Yeah.
Will we have a paper for those?
For this test, no. I believe on the final we give you some, and I can't remember which ones, but we do give you some formulas on the final. Okay. All right. Okay, so regular polygons. We talked about this a couple minutes ago. A regular polygon means all the sides and all the angles are the same, so it is both equilateral and equiangular. All the sides and all the angles are the same. Okay. And then we've got some other vocab kind of stuff here that we want to use, or that we'll use with polygons. We want to make sure we understand them. The center of a regular polygon, it goes in the middle, right? But to actually figure out where that center is, technically we're going to put a circle around the polygon, and the center of that circle is also the center of the polygon. So if I were to circumscribe a circle, if you remember that word from the circle chapter, right? And it's not the easiest thing to draw, but if you imagine this pentagon being inside a circle, right? If I then find the center of that circle, that is also the center of the polygon. So the center of a regular polygon is the center of the circumscribed circle. Circumscribed, remember, means draw around. So the circle's around the polygon. If I want the radius of a polygon, we're used to talking about radius with a circle, right? It's the same thing. If I make a radius of this circle, it's also the radius of that polygon. Now, if I make the radius from the center over to like any point on the circle, I could go outside the polygon. So I want to pick a spot in my polygon where it makes sense. So the radius will always go from your center to one of your vertices. So the radius is the distance from the center to a vertex. Okay. That's our radius. And you can draw that, in this case, 5 times around your polygon, right, to any of the vertices. If I draw another radius, then I create an angle, and specifically up here, I create a central angle. So that is a central angle in our polygon. Again, it's just like a circle. When we made central angles in our circles, the central angle of a circle is made by 2 radii. Same thing in a polygon. A central angle of a polygon is made by 2 radii. So it's an angle formed by 2 radii. In a regular polygon, we can make 5 of those central angles, and they will all be congruent. Okay, so we can say all central angles are congruent. In a circle, I could put them anywhere, right? But in a polygon, since I'm going, my radiuses are always in the same spots, they'll all be the same. Okay, then we have, let's do one more. I'm going to skip one and come back. So the measure of a central angle of a polygon, we just said they're all the same, right? And there are 5 of them in this case because it's a pentagon. Any guesses on how I find the measure of one of those central angles? If I looked at all of them, they'd go all the way around the center, right? So how many degrees would be all the way around? 360. So the whole way around is 360. And then I'm going to chop it up into the number of pieces I can make. In this case, I can make 5 because there's 5 sides. So it will always be 360 divided by your number of sides. So if I want the measure of that central angle, I'm going to do 360 degrees divided by n, and that n is your number of sides. Okay. And then we have one word that you've probably not seen before. I always like to ask people, how do you think you say this word? Everybody says it differently. We have a debate in the math office on how to say it. Way to go. Good job. I agree. Apothum, right? Some people say apothum. 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 So stupid. Apparently it's said both ways. So whichever is fine, right? The apothum of a polygon is not one of our radii. Apothum is where we go from the center and we're going to make it perpendicular to a side. That is our apothum. So it is the perpendicular distance from the center to a side. It's kind of like dropping an altitude in this triangle, right? And that triangle with our 2 radii, it's an isosceles triangle because the 2 radii are always congruent. So that apothum is always going to split that side into 2 congruent parts. So these 2 pieces will be the same. Okay, so we can say that your apothum bisects the side. And we get 2 congruent pieces there. Okay, radius, central angle, apothum. Those are the important ones. Okay. To find the area of a regular polygon, this is kind of what Savannah asked about this on one of the homework problems, right? They give you one of these to try to figure out on your own. We did one where we could have split it into a couple trapezoids. Doesn't work as well with a pentagon, but I could take this pentagon and cut it up into 5 different triangles, right? This purple triangle we made with the central angle, I could make 4 more of those and have 5 congruent triangles in my pentagon. Because it's a regular pentagon, all those triangles would be the same. So if I find the area of one of those triangles, and then I multiply it by how many triangles there are, I would get the area of my pentagon, right? The kind of shortcut way to do that is, if I think about area of a triangle, that's 1/2 base times height, right? Well, the height of this triangle is the apothum of our pentagon, right? The base of this triangle is a side length. So I would do 1/2 times the side length of the pentagon times the apothum of the pentagon. But then I want 5 of those triangles, right? Well, think about if I take a side length times 5 side lengths, what am I finding of that pentagon? That's not the area, it would be the perimeter all the way around, right? If I do 1 side length and then I add that up 5 times, I get the perimeter. So when I want the area of a regular polygon, we're going to do our 1/2 base times height. The height is the A, that's our apothum. And then the base is one of the sides, but then I'm going to take that side times 5 to get the perimeter. So I get the area of the whole polygon. So it's always 1/2 times the apothem times the perimeter of the polygon, and that gives us our area. Okay. Okay, so we're going to try some examples to see how this works with the different pieces. We're going to start with a square and a triangle. You have other formulas to do these, and that's totally fine. A rectangle or a square is base times height, or side squared. A triangle is 1/2 base times height, and then we just saw that other one, right? Side squared radical 3/4. But we can also use this 1/2 apothem times perimeter. Okay, you don't have to use any certain one, but I want you to be able to choose which one works the best based on the information you have. Okay, so let's try our first square, and these go horizontal, by the way. So this is one number, and this is our second one we're going to look at. Okay, so the first one tells us in our square that the radius is 5 radical 2. Remember, a radius goes from the center to a vertex. So if I put my center in my square, to make a radius, I would draw a line to one of my vertices. Okay, so this is 5 radical 2. We want to find the apothem, the perimeter, and the area, right? If I draw in my apothem, I would go from the center perpendicular to a side, and it cuts that side in half. And look what lovely shape we have made again and again and again. Right triangles! They never go away, right? Okay, so thinking about a square, we know that these are all right angles around the corners, right? And then in a square, when I draw in this radius, what do you think it does to that 90-degree angle? It cuts it in half, right? Because it's a square. So that means that this is 45 degrees and this is 45 degrees. So we have our lovely 45, 45, 90 triangle. The only rule we have for that is that the hypotenuse is equal to a leg times radical 2. Also, because it's 45, 45, 90, I know the two legs are the same, right? So I can call this x and I can call that x. That's one thing I think, there's only a couple of you in here, but I keep seeing that over and over again, like put variables on your picture. If there's something you have to find, put a variable there so you know that that's something you gotta find. Okay, so then if I want to solve that, I know my hypotenuse is 5 radical 2. That would be equal to x radical 2. So our x has to equal 5 just 5, right? Divide both sides by radical 2. So that means our apothem is 5, right? If x is 5, then what is the length of a side of the square? If this x value is 5, then what's the whole side? 10, right? So then a side would equal 10. So then our perimeter, there's 4 sides, so 10 times 4 is 40. And then to get our area, I know you could do the side squared, right? But just to practice, if I do 1/2 times the apothem, which is 5, times the perimeter, which is 40, well, half of 40 is 20, and 20 times 5 is 100. Ta-da! Which would be the same as if I did 10 times 10, right? Base times height would be 10 times 10 there, and give you 100. All right, let's do one more square. On the other side over here. Switch colors. Okay, in this square, it gives us the apothem, right? So apothem goes from the center perpendicular to a side. So this time we know that that is radical 3. I'm trying to find my radius, my perimeter, my area, so I'm going to draw in the radius as well. Same idea, it's another square, which means this is still a 45, 45, 90, right? So my hypotenuse is equal to the leg times radical 2. Well, if I know this leg is radical 3, then what's the other leg down here? Also radical 3. And then that means that our hypotenuse would be radical 3 times radical 2, which is radical 6. So that means our radius is radical 6. To find the perimeter, I need a side length. I know half my side is radical 3, so what's the whole side? 2 radical 3, just radical 3 plus radical 3, right? So a side length would be 2 radical 3. Then to get the perimeter, there's 4 sides, so 2 radical 3 times 4 gives us 8 radical 3. And then to get our area, we'll do 1/2 times the apothem times the perimeter. I know half of 8 is 4, and then radical 3 times radical 3 is 3, so 4 times 3 gives us 12 for our area. So exciting, I know. Okay, they're squares, right? Ta-da! Let's do the same thing with triangles. Yay! Maybe. My computer's stuck. Ugh, why? The screen shut off again. Let's see if it comes back. See if on the next one, while I'm waiting for this to come back on, draw a radius and an apothem in your triangle. See if you can put them in the right place. Radius goes from the center to a vertex. Apothem goes from the center perpendicular to a side. There it goes. Came back. Easy? Thanks, Jack. It is easy. There's my center. Here's my radius. Maybe. Did it draw? Come on, computer. Let's try again. Radius is 8. Apothem goes there. Yeah? We put them in the right spots? Okay. Okay. So again, we've kind of made this little triangle, this time inside of our triangle, right? When we had the square, we had 90-degree angles that we cut in half. When I have a triangle, what kind of angle am I cutting in half over here in this corner? 60. It's a 60-degree, right? They all have to add up to 180. So if I cut that 60-degree angle in half, that means that's a 30-degree. And so we get our lovely 30, 60, 90 triangle. Yay! So we can do hypotenuse equals 2 times the short leg, and long leg equals the short leg times radical 3 are our rules. I'm just going to call them x and y. That way I know which ones I'm solving for. Remember, your short leg is across from the 30-degree angle. So x is the short leg. Y would be my long leg. So I can do the hypotenuse, which is 8, is equal to 2 times x, which means our x has to be 4. And then long leg is y, would be, we now know our short leg is 4 times radical 3. Okay. X was our apothem, so x is going to, our apothem is 4. To get our perimeter, we want to add up all three sides. If I know that y is 4 radical 3, then what's the side length? 8 radical 3, right? So a side would be equal to 8 radical 3. And then to get the perimeter, I want to multiply that by 3 for our triangle. So it would be 24 radical 3. And then for our area, we can do 1/2 times the apothem times the perimeter.
Oh, this works for like every single shape.
It works for as long as they're regular. So it will only work for an equilateral triangle, right? Not for every triangle. Good question. And it only works for a square, not all rectangles, right? Okay. So what's that? 1/2 of 4 is 2. 2 times 24 is 48 radical 3. Ta-da! Okay. I got that one. Okay. Another triangle. This time it gives us the perimeter is 6 radical 3. So what's that mean about each side? 2 radical 3, right? If I divide by 3 sides, it's all good. So 2 radical 3, 2 radical 3, and this one would also be 2 radical 3. I want my radius and apothem, so I'm going to draw them in here. There's our radius. There's our apothem. If I know this whole side is 2 radical 3, then that would mean that this piece is just radical 3, right? Because it'd be half of it. So we know each of those is radical 3. And then I'm looking for my x and y, right? We can label those. Again, we know this is a 30 and this is a 60. So we're splitting that equilateral triangle angle in half. Stop it. There we go. So then my long leg is radical 3. My short leg, my long leg is equal to the short leg times radical 3, right? Let's see, we'll write it down here. So long leg equals short leg times radical 3. So radical 3 equals x times radical 3. So that x just has to equal 1. And then my hypotenuse is the 2 times the short leg. So y would be 2 times 1, which is 2. So then our radius is 2, and the apothem is 1. And then to find our area, 1/2 times the apothem times the perimeter, and we get 3 radical 3. Okay, so that's how it can be used in a square and a triangle, right? Remember, it can only be done, that formula can only be used if it's a square or if it's an equilateral triangle, not just any triangle. The one we'll use this the most for are pentagons, hexagons, octagons, decagons, whatever they are, right? Because we don't have another formula for this one. Okay, so same idea. Let's draw in our center. I'm going to make a radius and an apothem, which again makes our right triangle there, right? And for this one, we know the radius is 8, right? Okay, so in our square, we knew that diagonal cut that angle in half, and so it made it a 45, 45, 90. In our triangle, we cut the 60 in half, so it made it a 30, 60, 90. For our polygons, sometimes it's easier, instead of thinking about this angle down in the corner, if we think about that central angle up on top. So if I draw in another radius here, right, and then I think about that central angle, remember your central angle is 360 divided by the number of sides. So in our case, we have a hexagon. So if I do 360 divided by 6 sides, then I know that that central angle is 60 degrees. That altitude cuts that in half, so that means that this part is 30. And then we get our 30, 60, 90 triangle again. We use them a lot, right? Hopefully you can start to get the rules a little bit quicker. If this is my hypotenuse, in this case, this will be my short side. This will be the long side. The hypotenuse is equal to 2 times the short side. So if the hypotenuse is 8, that means that our side down here is going to be 4. And then the long side, or the long leg, is the short leg times radical 3. So that would be 4 radical 3. So our apothem is 4 radical 3. Remember, your altitude or your apothem splits your side in half. So if that piece is 4, then this piece is also 4. So our side lengths are 8. There are 6 of those, so our perimeter would be 8 times 6, or 48. Notice here that your radius and your side length are the same. That only happens in a hexagon, okay? Where your radius and your side length are the same, that only happens in a hexagon, not in like pentagon, octagon, and so on. Then to find our area, we can do 1/2 times the apothem times the perimeter, which would give us, what's that, 2 times 48 is 96 radical 3. Okay. Okay. The other one like this goes, no, that's fine. Goes pretty similarly. I want to, since we've only got about a little less than 10 minutes or a little more than 10 minutes, I want to skip ahead a little bit and go to part E, which I think is the very last problem. Go all the way to E. And the reason I want to do this one is it's not a hexagon, it's a nonagon. How many sides does a nonagon have? 9 sides, right? It's really hard to draw. I'm really bad at drawing nonagons. You can try your best, or you don't really need to draw the whole thing in this case. So a nonagon, whenever it's an odd number of sides, you always want a flat bottom, and then you want to make a point at the top, is one way to think about it. But like I said, nonagon can be kind of hard. So there's 1, 2, 3. You got to do, I always draw it wrong. Let me look at my picture again. It's more sides than I always think it is. Then I'm going to kind of go up and up. And you kind of go this way and this way and this way and that way and that way. It's not a very good nonagon. It kind of looks like a circle, right? I think I did 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I did 11. Dang it. I did too many. Like I said, not easy to draw, right? But it's okay because you don't really need the whole shape. I think now I got it. That one and that one. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Do your best. Our nonagon has 9 sides. And it's telling us the radius is 10. So if I make the center of my nonagon and I draw in a radius, that length is 10. To find my area, I want to do 1/2 the apothem times the perimeter, right? Right now I only have the radius. I don't have either the apothem or the perimeter. So if I draw in my apothem, it would go here, right? So I need to find that. I'm going to call that x. And then to get my perimeter, I need a side length. So if I call that y, that's half of my side length, right? So if I get x and y, I'll get everything I need to find the area of my polygon. Okay, so really, I just need to solve that right triangle. Right now, though, I only have one side. I can't do anything if I only have a side. I can't get the other two sides, so I need to think about my angles, right? So we're going to do the same thing we did with that hexagon, is if I draw in another radius here, I can think about this central angle of my nonagon. So to get that central angle, I'm going to do 360 divided by my number of sides, which in this case is 9. So that means 360 divided by 9 is 40. So that angle is 40 degrees. Right? It'd be easier. I can actually draw it in there. 40 degrees. Okay, now what I recommend on these is draw the triangle out by itself. So I'm going to pull this triangle out so I can see it better. Here's my right angle, right? I know this side over here is 10. I called that x and that y. And then we found this central angle up here is 40 degrees. So what's that telling me about this angle in my triangle? It'd be half of that. So then this angle is 20 degrees, right? Which also means down here, this one would have to be 70, right, to add up to 90. But I really only need one of those angles. This is not a 30, 60, 90 or a 45, 45, 90. So what do we have to use instead? We're going to use our SOHCAHTOA rules this time, right? So the 10 is the hypotenuse. If I'm going to use 20 as my angle, then y is the opposite, x is the adjacent. And then we can use our trig functions to solve for x and y. Let's say I want to solve for x first. That's my a, and I know h. So if I have a and h, which trig function am I going to use? That'd be cosine, so SOHCAHTOA, right? So I'm going to do cosine of 20 degrees would be equal to my adjacent, which is x, over hypotenuse, which is 10. I can multiply both sides by 10. And then if we type that in the calculator, we get x equals 9.3969. Like I said, keep about 4 places on these. That way you don't create too much error. To find y, I'm using the opposite in the hypotenuse. That's our SO of SOHCAHTOA, right? So I'm going to do sine of 20 degrees would be our opposite over hypotenuse, so y over 10. And again, multiply both sides by 10. And we get y equals 3.4202. So when we do our area, we need apothem and perimeter, right? X is our apothem. We've got that part. We're all set. This is our apothem. We need a side length, though, right? We said y down here is actually half the side length of our nonagon, right? So to get a side, I want to do that 3.4202 times 2, which is 7 something. 3.4202 times 2. Oop, that was close. 6.8404. So then to get our perimeter, I'm going to do that times 9. Because we have 9 sides. So that's 61.5636. Okay, then last step, our area would be 1/2 times the apothem times our perimeter. And if we put that in our calculator, we get 289.25. There's a lot of steps, but if you keep track of what you're doing, it's not that bad. We won't do a whole lot of these, but just know if it's not a hexagon, you're going to have different angles in your triangle here. So you have to think more about that and use your SOHCAHTOA instead of those rules. Okay. I don't know if we'll go back and do the other ones, but I will write them down at least so that they'll be in OneNote if you want to get the other examples on here. But it's the same idea. It's another equilateral triangle, a square, a regular hexagon, just like we did before. I wanted you to see the ones that are different. Okay. Homework is in the book again. It's shorter even still, right? They keep getting a little bit shorter, but you see how you've got the 3 tables? You do some practice with the square, practice with triangle, practice with a hexagon, and then you've got a couple other on the bottom, I believe. Okay. Okay. I guess I can stop this now. Hopefully it recorded. Yay.